So here's our next problem. What I have is a 20 kilogram disc and a 10 kilogram block. Okay. And so we can see there's a rope tied to the disc over the pulley, then around this pulley, and it's attached up to the ceiling. And that's supporting this block. All right. And the question is, find the minimum static coefficient of friction here such that, that's what that backwards epsilon symbol means, the disc will roll without, here's the without, slipping. So we want to have just enough friction in here so this disc will roll without slipping. Now, what is that? We've done stuff like this in exams before. Again, it doesn't go so well. And the problem is they're not quite sure how to handle this μs. So we're told it's the minimum amount of static friction. Okay? So we will note that when you're dealing with static friction, a system will provide as much as it can up to a maximum, but you never quite know what it is. Well, in this case, we do, because there will be no extra available. If this could be smaller, it will keep getting smaller until it can't get any smaller. All right, so friction, the static friction will be, in this case, μSn. All right, because if the friction is less than that, it means we could reduce this further. Okay, so we know the friction in this case. It will be μSn. We're just going to find the smallest one that works inherently. All right, so let's take this then to the free body diagrams. And so relative to the disc, there's a tension in the rope. We have the weight. The normal force will be right up through the point of contact. We'll call that point of contact A. This is rolling without slipping. So recall what we did with rolling without slipping. Point A, its only acceleration would be up. Okay, it has relative to the tangential, x, it is still. A sub x is still. It has no x acceleration. All right. To get this thing to roll, it'll roll like this. That'll be driven by friction, so we call that Fa, which is μSn, and then there's the normal force again. B, that's down here. It's supported by two ropes, both with the same tension, and it weighs 10 times gravity. So there are the free body diagrams. Let's start finding the equations. So we'll start looking at the disc first. And, oops, we'll go to take it all the way to here. All right, this is a disc. So Ig is 1/2 mr squared. We know mass, we know r, it's here at 0.2, so 1/2, 20.2 squared. We have 0.4 kilogram meter squared for mass moment of inertia. So if we sum the forces here, which is the logical approach to take, all right, we would have the only torque, that's due to friction. That's going clockwise here, so minus μs times the normal force, that's 20 times 9.81. All right, then we have the radius here to make it the torque, times 0.2 equals. Then we have mass moment of inertia times alpha. So that's just filling in the equation. Now, if we look at this problem where we are, we have one equation, two unknowns. All right. Now, we're going to look at the disk one more time, and we're going to sum forces in the x. So we have a force T here going in the positive x. Friction goes in the negative x, so μSn. All right, equals mass times acceleration of the disk in the x, which is going to be it will have no acceleration in the y. All right, it's not falling through the table and it's not jumping up. So, but doing this, we added another equation and two more unknowns. So we have 1, 2, 3, 4 unknowns, two equations. All right, so now we're going to go over here. We'll sum forces in the y. So we have 2t up minus 10 times 9.81 down, and that will be mass times acceleration in the y for the block. So let's see, we had 1, 2, 3, 4. Now we have 5 unknowns, 3 equations. We need 2 more equations to make this thing work out. All right. So where are we going to get them? Well, as is typically the case, we're going to start appealing to kinematics. So we need to start thinking about stuff. This is rolling without slipping, so down here, the acceleration along the x here is 0. That's part of rolling without slipping. Remember, we had this path. It comes in, and then it goes straight up and out. Okay, so acceleration, ax, which is on the wheel, 0. We've had that. All right, so what's the acceleration of g in the x? Well, we've done that before, and that's just discussed here. Agx would be nothing more than alpha cross r from a to g. So that's very nice because it relates agx, one of our unknowns above, to alpha. So if we find agx, we get alpha, we get alpha, we get agx. So one more equation with no more unknowns. That's great. We just need to do this one more time. So what do we need to do here? What we need to do is relate the acceleration of the disk, the center of the disk, to the acceleration of b. Well, we can do that just off of this rope. The motion of g exactly determines the motion of b. All right? So this is right here. Using our normal equations, if we were to measure dg, that's this, from here over to there, and then we have dB, that would be from this point down to here. So we have dg plus 2 dBs, there's dg, equals a constant. Take the derivative twice, and we can relate acceleration of b to the acceleration of g. And so we're all set. Here's your sixth equation. We now have 6 equations, 6 unknowns, and it's an algebra problem. I'll leave that to you. You can check the results, but when you go and solve it, you find US has to be 0.0769, or anything greater will work. We'll catch you later. One more problem to do.